First of all, thanks, Andrew, for accepting our invitation to this talk. It is a real pleasure to have you here today. Besides, I just realized you are on holidays, and even though you accepted to give this talk, so I really appreciate that. This is a very special colloquium because we are about this is the anniversary of CIO colloquium. We wanted to contribute to this anniversary by inviting Andrew. We planned this since a very long time. Laura and myself wanted to have Andrew, and fortunately, he is willing to give a talk to CIO. And I also thank you guys for joining us on this very special occasion. Andrew doesn't really need an introduction. Everybody knows Andrew, at least everybody who works in photonics knows Andrew around the world. I just want to say a few things before I hand the mic to you, Andrew. Andrew is now, well, his main research line is structural light. His research revolves around structural light, from its generation, manipulation to its many applications at both the quantum and classical regimes, in optical tweezers, in optical communications, and so on and so forth. He is now a distinguished professor at the University of Witwatersrand in South Africa. He's been there since 2015. I've had the pleasure to work with Andrew and continue on many collaborations. It's a real pleasure for me. Andrew has won a lot of prizes, many prizes. He publishes at least 20 papers per year, so he's very active. And the one thing I love about Andrew is that he's promoting photonics in South Africa. He's one of the, has contributed a lot in South Africa. And so your reputation, as I said earlier, Andrew, your reputation precedes you. You don't need any more introduction. Please, thanks a lot, Andrew, once again. And please, you can start whenever you want. I will stop sharing now my screen so that you can start sharing yours. And thanks a lot, Andrew.
Great. Thank you very much, Carmelo. I'm going to switch off my video. Okay, with a bit of luck, you should be seeing my slides. Can you just confirm that, Carmelo?
Yes, we can see your slides, Andrew.
Great, fantastic. All right, so thank you very much for this invitation. I really do appreciate it. In fact, I've been to Mexico on a few occasions, and I've been to the CIO twice. So this is, I guess, my third visit, but this time only virtual. And as Carmelo said, I'm at the School of Physics at the University of the Witwatersrand. So let me just show you where I am. Hopefully my signal stays strong throughout this talk, but if it doesn't, just shout and I'll go back a slide or two. But here I am at the bottom of Africa. And actually at the moment I'm not at my house, I'm in Durban. I'm visiting my mother as it happens, so that's why I'm not so sure about the signal. But this is also where I studied. So it's a surfing town, it's a beach town, very beautiful for holidays. I used to work in Pretoria, and I presently live just a little bit outside Pretoria. It's the capital of the country. And if you take a 30-minute train ride south to Johannesburg, you find the financial capital of South Africa, Johannesburg. And that's where the university is. Actually, the city is not very pretty, but if you go out into the suburbs, then Johannesburg is actually the largest man-made forest in the world. So it's very, very pretty out in the suburbs, but you have to come back into the city to find the university. And then here it is. It's the University of the Witwatersrand. It's pronounced with a V because it's a Dutch name. So we just call it Wits. And it's produced 4 Nobel laureates, and next year it will be 100 years old. And if you come a little bit to the left of this great hall, you find the School of Physics, and inside the School of Physics is my lab. And it's, of course, we work on structured light, a variety of different approaches. So I assume that there are quite a few students in the audience, so I've made this a fairly tutorial style talk, but with something for the researchers as well. So here is my tutorial cartoon of what I mean by structured light. So imagine that I have some blob of light, maybe a laser pointer or a Gaussian beam. In principle, can be anything. And I want to convert it into something else, say a smiley face. This is what we mean by our structured light. And what we do is we say, well, how do we get the structure into the light? And the question can be phrased in this little cartoon equation. And basically we say, well, knowing what we have and knowing what we want, what do we need to put in between to execute this transformation? And that's all we do in our group, essentially. And once you find the answer to the problem, then you can implement it by a variety of methods. And usually the solution is somehow linked to the implementation as well. So for example, I could say, well, why don't you just take a piece of glass and a black pen and block out everywhere you don't want light? Then you would get a smiley face as your transmission function. So that would be amplitude shaping. Of course, it would work, but it would be very lossy. Instead, what we tend to do is we use interference is our method. So we say, look, everywhere that you see light, we want constructive interference. And everywhere that you don't see light, we want destructive interference. And now the question is how to calculate the phase map that lets you do that. And once you calculate it, you can implement it with geometric phase, with metasurfaces, or diffractive optics, or holograms. It's up to you. And we don't only want to do it with the amplitude of the light. So here you see the intensity patterns, but you could do it also in the time frequency domain. You could do it purely in phase, and you can do it in the polarization degree of freedom of light. Now, if you're a student in the audience, you're probably wondering, but hang on a second, how do these different degrees of freedom lend themselves to this idea of interference? Let me go back 200 years, and here's Thomas Young, and I would say that his experiment with the double slit was the first example of structured light. Maybe not the most exciting example, but he certainly structured light, getting interference fringes across the beam. And we all know how he did that. It's the path difference between the two slits that give rise to constructive or destructive interference. And so now here's a question that I typically ask my third-year optics class. I say, well, look, what Young did was he showed that you could add light to more light, and the result could be darkness. And we know that's possible because the electric fields can cancel in some places. They can point in opposite directions. But if you have two different polarizations, well, then we know from Pythagoras that the only way the hypotenuse can be zero is if you have your case that you've got no light in the first place. So that's not very interesting. So assuming that we have got light in these two polarization states, is it possible to get fringes? And the answer is yes, but you need to know where to look. So the fringes in the double slit experiment would be this. You can see that there are fringes, but not in the intensity of the light, but in the polarization state of light. This message of structuring light by interference is valid for all degrees of freedom, but you may have to have a little bit of care in where you look for the fringes. In fact, this very nice plot was done by a visiting Mexican student to our group, Ben Perez. He's now at Tec de Monterrey. We have a very nice tutorial style article explaining this concept. Okay, so we can use interference. How should we implement then the solution that we find? Well, historically, we have used spatial light modulators. They are little liquid crystal displays where maybe there's about 2,000 by 1,000 pixels. Each pixel is filled with liquid crystals that we can rotate. And based on the voltage applied, you get a rotation which can be calibrated to a phase change. So in the rest of this talk, if you see a color going from black to white, we mean a phase change from 0 to 2 pi. And now, in my opinion, Mexico have actually led the way in how you go about calculating and implementing these holograms. Think of people like Victor Arizona and many, many others. And basically what it means is that even though a spatial light modulator only lets you change the phase, I can do arbitrary amplitude and phase control. So in fact, here is the hologram that generates the smiley face. And more surprising is that by playing some Fourier tricks, you can make it work a range of wavelengths. So there's this belief that spatial light modulators are wavelength dependent. True, but also not true. You can make it work across the entire visible spectrum by just playing a couple of simple tricks. And so if you want to know more about that, in fact, our host today is the expert. Carmelo and myself put together a nice book. I think SPE get all the money and we get like 1 US cent for everyone that's sold. But it is a very useful book if you want to get going very quickly in this field, because Carmelo has put all the MATLAB code into the book so that you can immediately start. Well, today we move away from spatial light modulators in my lab because they're quite expensive and they're a little bit slow. And so we tend to use digital micromirror devices. So they're in fact, exactly the devices you see in your projectors, little micromirrors. Now they're an amplitude only tool, but by playing the same Fourier tricks, you can make them work for phase and amplitude control as well. And here you see one of my master students has generated a whole spectrum of structured light beams. These are experimental images, and they're all produced on this digital micromirror device. Okay. So if you play with whatever tool you want, whether it's a DMD or an SLM, and you go to the lab, and here you see Angela in the lab, and she's using a spatial light modulator. In this case, you can generate, in principle, any structured light field you want in any degree of freedom. And you know, when I got going in this field many years back, it was people like Julio and Sabino and many, many others around Mexico that really were leading the way at that time. And their seminal papers, in my opinion, paved the way for the rest of us to follow. So I really have to tip my hat to the leaders in this field. Okay, now let me go back to the inference argument now from a slightly different perspective. And that perspective is going to be the structuring of lights, 1 or 2 step approaches. So what do I mean by that? Well, here's my bulb of light again as my input field. Imagine it's Gaussian, but it doesn't matter, actually. You can redo this example for whatever you want. And imagine I have a flat phase. Well, I can create my desired field in amplitude and in phase in a single step, but then it must include loss. So you can understand that if you want to control the amplitude here, you would have to have some sort of amplitude control as well. And so lossy structuring of light can be done in 1 step. If you want to do it lossless, so in principle, don't lose any light, you can still do it in 1 step, but you can only control 1 degree of freedom. So for example, let's say you wanted to convert a Gaussian beam. You can do it by interference in 1 step, but you have to leave the phase as a free variable. And if you want to correct the phase, you can do it with second elements. And so if you want loss of light, you need at least 2 steps. And so I'm going to show you this principle throughout this talk. And to do that, I must pick some pattern that we like to use. And although I won't only use orbital angular momentum, it is the one we use the most often. And we use it because it's easy to create and it's very intuitive. So let me give you my 1-slide tutorial on orbital angular momentum. So here is the Gaussian beam I showed you earlier. It carries no orbital angular momentum. And near the waist, we would have plane wavefronts. Of course, if you go away, the wavefront becomes curved. But let's just consider near the waist for the moment. And now what I can do, I can twist the wavefronts by 1 twist per unit wavelength. And if I do that, I get a helical wavefront. The phase is not defined in the center, so I have an intensity null, so I have a donut-looking beam. And now it carries 1 unit of orbital momentum. And I could twist it twice, so 2 twists per unit wavelength, or 3 twists and so on, and you see that the hole gets bigger and the structure of the phase becomes more complicated, looking like fusilli pasta. And if you've been paying attention as one of the students, you would have seen that I twisted only in one particular direction. but I could change that direction. So twist clockwise and anti-clockwise. And as I go in the opposite direction, I go negative in how much orbital angular momentum the light can carry. So that's my favorite pattern that we're going to use in this talk. So let's use it now to understand this principle of 1 or 2 step beam shaping. So if you know anything about orbital angular momentum, you'll know that if you bring this blob of light, the Gaussian beam, into, say, a spiral phase plate made of glass, or a hologram that is the equivalent, so it goes from white to black around the azimuth, that gives it one twist. Well, then we get twisted light coming out, and this is what we would say is a vortex beam. You say, but you've just contradicted yourself, because look, this is a phase-only approach. It's done in 1 step, and everything looks perfect. But in fact, this is not what happens in reality. In reality, this is what you get. Now, you don't see this very often, because usually when people show you pictures of their vortex beams, it's very low orders. In fact, this is an order of over 100. And so now you see all these many, many rings of light. Those are radial modes. So you see a phase-only approach gives me the desired phase, but leaves the amplitude as a free variable. And to correct the amplitude, which I've just done now experimentally here, I need 2 steps, or I need a lossy process that controls both the amplitude and the phase. So these principles hold for all types of beams. It's just that we sometimes blatantly lie, show readers in our papers what the beams really look like. Okay, so we can create OAM beams in the lab very easily, and the process of creating them is consistent with what we've seen. You naturally ask, well, how big could you go with SLMs or DMDs? Now, some years back, Carmelo showed that you can create about 200 modes on a single device. So those are 200 different modes. And here we ask a little bit of a different question, and we say, well, how big could each mode be? And you can calculate, actually, theoretically, that for a typical device, it depends obviously on the pixels and so on, but for a typical lab-based device, the number comes out around about 600. And you can confirm that experimentally as well. So here you see experimental images from a SLM, actually, of about 600 OAM. Again, this is created with amplitude and phase control. Although this simple principle of 1 or 2 step shaping is a general rule, of course there are lots of special cases, right? And here are some of my favorite means of creating orbital angular momentum and vector superpositions of that, using, for example, holograms and liquid crystals, metal surfaces, even glass cones and liquid droplets. So there are many exceptions to the rule that appear to break it, but they still actually hold that general rule. And if you want to know more about that, there's a nice review paper that covers all these different ways of doing things. Okay, so why would you want to structure your light? I mean, I chose orbital angular momentum as one example, but of course there's many examples of structured light. Why would you want it? Well, here are some of the obvious applications, and I like to phrase it as pushing the limits in what you can do with light. So, for example, using lots of patterns of light lets you extend the bandwidth of communication systems, or structuring the polarization of the light. In this example, being radially polarized lets you do sub-wavelength focusing, so getting light smaller. You can also see better if you use structured light as your detection. So all of this is being kind of on the creation side, but this is on the detection side. So rather than detect images with pixels, why don't you detect in a basis patterns? If you do that, then you can get sub-wavelength imaging. You're not breaking the rules of Rayleigh and Arb, you're just breaking the assumptions that they put in place to create those rules. And if you break the assumptions, then of course the rules don't hold. And of course you can get extended range and things like light sheet microscopy if you change the type of structured beam that you use. So you can push the limits in a whole range of applications. And I'm not going to show anything in optical trapping and tweezing. Again, I feel that Mexico, along with Scotland, have been sort of the leaders in this field. Many, many people have done fantastic things that I read at the very beginning when I also got into this field. And of course, there are some amazing things that people have shown with it. I mean, if you think of STED imaging uses structured light, but in a non-linear way in order to see really small things. You can narrow structures with structured light. Combining light with near field effects lets you do things at scales at the very, very small. And here are some beautiful images, as well as this one from my colleague in Prof, who plays with big high power lasers, and they use structured light to do exotic structuring of matter. So extending the functionality of what you can do with light and combining light with matter seems to be the compelling frontier that people are pushing towards. I'll give you one example of changing our paradigms a little bit, changing the rules. And this relates to beam propagation. So here I show you the cross-section of a flat top beam, and it's going to propagate in the Z direction. And as most of you will know, as you propagate a flat top beam, it becomes very, very complex in its intensity pattern. So it doesn't stay flat top for very long. And this is the problem because in laser materials processing, it would be wonderful to have a flat top beam. It's the perfect beam for many materials processing applications, but then delivering it to the target is problematic. For example, you can't just focus it, the beam will change dramatically. All right, how can structured light help you with this? Because this is already a form of structured light. Well, we can use another degree of freedom to make a flat top beam that stays flat top in principle forever. How could we do that? Well, we could add a Gaussian to a vortex beam, but add them with orthogonal polarizations. That way, the Gaussian kind of fills in the hole, and you get a flattish beam, not a perfect flat top beam, but a flattish beam. And so by playing a little trick with another degree of freedom of light, we can break some propagation rules. Now, nature never gives you anything for free. So what do you have to pay for this? Well, what you have to pay is that across the field, which is shown with these red and blue circles representing left and right circularly polarized lights, becomes very complicated. So if your process is not polarization dependent, so you're fantastic, you've just got the answer to your problem. If you do care, well, then maybe this is not the answer to the problem. The point is that by going to the structure in all degrees of freedom, you can push the paradigms and in some cases change them. And one of the areas where I think the future really lies is in the combination of structured light and non-linear processes. Everything I've shown you up to now has been linear, but really amazing things can be done if you change that to a non-linear structuring system. And there have been some fantastic recent works out from Ottawa, from Harbin, showing you some, and from Brazil for that matter, showing you some really exotic structuring. It's totally unexplored. And if I was a student today, this is the area that I would go into. So let me go to something that's very close to my heart, and is also in its own way a certain type of nonlinear process, and that is a laser. And what I like to do is I like to look at ways to structure light inside lasers. So everything I've shown you up to now has been, I give you some blob of light from a laser and you restructure it to something that you want. Okay, so let's see how we could build a structured light laser. So first we have to build the laser. And fortunately, there's only 3 things that you need to build a laser, although putting them together. So the first thing we need is a medium that has the potential for optical gain. In other words, you give it a photon, it gives you more photons back. We know that materials don't do that under equilibrium, so we have to get the medium to get it out of equilibrium. So we need an excitation system. So that's number 2. a medium, and a way to get it excited. And what's the third thing? We know from Einstein's rules that stimulated emission becomes the photons around. So great, we put our photons in a box. We make the box of mirrors, so the light bounces back and forward. And so we have an optical box, a resonator, and that's the third requirement. And now what we're going to do is we're going to do our 1 or 2 step beam shaping by putting elements inside this box and see whether we can get some form of structured light out according to our design. You know, this has been done already back in the 60s. And if you think of people like Kolgalnik and Lee and Fox, actually Tingye Lee was a graduate from our university at Wits. And he wrote those famous papers with Kolgalnik and Lee and Fox and Lee. And what they did was they basically did a 1-step amplitude approach. And for example, to get Hermite Gaussian beams, they just put wires inside the cavity. So that's the 1-step amplitude lossy process. And indeed, it works perfectly. Actually, very recently, a group in Munster did a beautiful experiment. They used a DMD at the outside of the laser to shape the gain. So here is their hologram. They used it to excite the gain in this particular shape. And then the lasing mode, of course, follows where there was gain, because lasers balance gain with loss. So controlling one is equivalent to controlling the other. But that's a bit of a lossy way of doing things, but it still works. Here's another example of a laser that I showed you just one slide back. Let me go here. So here you have the amplitude mask, and it dictates what's going to come out. Here is the same box, just shown as a cross-section. I've got a mirror on the one end, and I've got a mirror on the other end. And here I'm going to put some amplitude mask over here. Now, I can use the curvature of the mirrors and the length of the laser to make sure that there is a net magnification inside the box, because the mirrors don't have to be flat. So what does it mean? It means that if I start light, say, at this dashed line, and it goes once around, it comes back, it's either magnified by a factor M or demagnified by a factor M. And obviously, each time it goes round and light bounces many, many times in the laser, then you get, you know, this magnification happening all the time. So then, of course, you can see that what's going to happen is that you're going to get structure within structure. And it's all main. Well, we have a name for things that have structure within structure at infinite dimensions, and they're called fractals. Oops. Carmelo?
Yes, your PPT, right? Your PowerPoint just.
It just.
Turn up.
Yeah, I don't know why. Just give it a second.
Yes, no worries.
Well, while I wait for that just to come back online, it'll take a second.
Yeah.
So you get structure within structure, and that's exactly what we call a fractal. So the idea is that with a very simple aperture, if you just choose the curvature of the mirrors correctly, you can actually get very complex structure from that laser. Okay. All right, let me just open it here. Okay, can you see that again?
Yes, we can see it. Yeah, we're back.
All right, good. Sorry about that. Hopefully it doesn't happen again. And so here it is. So here you have very complex fractal light, and it's directly from a laser. Now that would be the amplitude shaping. What about the phase shaping? Well, again, that was done in the 90s by many people. And the idea is that you have a phase mask at one end of the laser, and you design it so that you get some form of structured light coming out of the box. And here you see some example patterns of that. This was done in the 90s because people invented things like diffractive optics and so on, and so it was possible to these structures. And I think by Frank Warofsky, and he designed a phase element that would give you a lambda sign as the output from the laser. He didn't actually make that laser. It was just a numerical example, but still I think it's a pretty cool example. One day, well, look, if you're going to have a single phase, why don't you just make the mirror a spatial light modulator? That way you can change a hologram, which effectively changes this mirror's properties. And it's digitally controlled. And the result, and here you see some experimental images, are many, many types of structured light that come out of the same laser. And if you've ever built a laser before, you'll know that usually every time you want to do very careful alignments, here there's no alignment change at all because nothing is changing physically in the cavity. It's only a picture that is changing. Now that, of course, doesn't work at high powers. And here I show you a picture of a long, long time ago, and I'm showing this to the students to make the point that not everything is about publications. Sometimes it's about applications. And if you have such a big high-power laser, then it turns out that if you use amplitude control, for example, apertures, you can get a beautiful beam, but with very low energy. Or you can get a very complicated, ugly beam, but with lots of energy. And if you try to use it for your application, in this case, it's paint. It's trying and white paint a green undercoat from a metal surface. You see that the structure of the beam gets imprinted in the process. And so now you can design a mirror that can handle high powers. It's a phased mirror. It's got a structure to it, although you can't see it with your eye. You get a compromised beam, and now when you run the process, you see that whereas previously I still had lots of undercoat while I was damaging the metal, here I've cleared it very nicely. So this particular work, no journal papers associated with it, but it became a product that now sits on the production floor. So structured light doesn't have to be orbital angular momentum, and it doesn't have to be journal papers either. All right, so if you've been listening carefully, then you would have realized that we only used a one-step process in all of those examples. And so you might say, well, would there be any value in having a two-step process if you have a laser? And there is a value, excuse me. It is that if you have two phase elements, so a two-step shaping problem, you can define the shape of the light at both ends of the laser. So you can define it at this end and at the output end. Remember that the end is usually where you have the gain medium. So in other words, you can specify the light at the gain side and what comes out. That means I could specify the beautiful beam as the output, but specify a pattern that gives you all the energy. And this we've shown experimentally, and so you see that, don't worry about all the details, but you get a very beautiful beam coming out of the laser. It's this one over here, whereas it would have been a rather ugly beam, but this beam, this perfect Gaussian, has all the energy of the, and so this is an approach towards high brightness lasers. But it's surprising if I go back to my famous and popular example of orbital angular momentum, that these tricks don't actually work very well inside lasers for orbital angular momentum. And the reason is that the laser can't tell the difference between a left-handed twist and a right-handed twist. They look absolutely identical to nature, and so it can't tell them apart. And so it's actually counterintuitive, but you need to break the symmetry of the laser in order for it to laze on orbital angular momentum states. And these are some, well, this top one is our own work using geometric phase, but there have been solid state lasers in the top row, in fiber lasers in the middle row, and on little chips in the bottom row. And you will have these slides, and I encourage you to go and read these papers. There's some beautiful ideas out there. Our most recent one, so what we did was we took a meta surface that modulates both the geometric and the propagation phase of light. And with 3, so let me show you what that metasurface looks like. So here it is. And so this is a nanostructured surface, structured matter essentially, being used to structure light. And what it does is it allows this laser to work across 2 very different OEM modes. So on the little right, you see an animation of a model of the laser converging to an OEM mode, starting from noise. And then as I rotate the metasurface, I can make this laser on an L10 mode that's horizontally polarized, going all the way around to an L100 mode. And somewhere in the middle, it's lasing on both. So these are highly asymmetric OEM modes coming out of the same laser. And because they have different polarizations, we have a vector state out of this laser. So at this point, I've probably given you the notion that, if I go back a couple of slides, that if you want structured light out of, then you need a very complicated solution, maybe a complicated box or complicated elements inside the box and so on. But now I want to ask a question and say, well, does it really have to be complicated? And what if I wanted to make the solution much more exotic? So everything I've shown you, including this very nice example here, there's only 2 degrees of freedom that are being controlled, the spatial mode, the OEM, and the polarization. That is kind of depicted in this little picture here. It's a typical vector beam. But what if I wanted many degrees of freedom, not just 2? Where would I find them, and how complicated would the solution look? So I'm happy to tell a few cases where nature plays along, and the solution is actually very, very simple. So here's my cartoon of a laser again. You see the curved mirror at the top and a flat mirror at the bottom. And all I'm going to do is change the distance between the 2 mirrors. So as I go across here, you see that the gap is getting bigger and bigger and bigger. And what I'm drawing in red are the trajectories, the ray-like trajectories that would be stable in that type of cavity. It's like an undergraduate tutorial exercise using ray optics, which rays would keep repeating inside this little box. And this is what the answer looks like. So at very, very specific distances, the laser jumps into a mode where it actually looks like rays coming out of the laser, but they're not rays. It's actually one coherent paraxial beam. But I can now use a trick from quantum mechanics and say, well, why don't I mark these rays as paths? In quantum mechanics, we mark the paths all the time. Let me do that here. So I'm going to build the laser, and it's really nothing more than just 2 simple mirrors and a gain medium, something you could find in any undergraduate lab. And I'm going to adjust the distance to make it jump into this little trajectory. That's, by the way, what a laser looks like in our lab. It doesn't look like the box that you buy from Newport or Coherent, but it works. And here it is. So here I show the 2 mirrors in like kind of semi-transparent, and the blobs of light is actually measurements inside the laser, verifying that it's doing this ray-like trajectory. And now we can control the polarization of each individual path because it arrives at a crystal at a slightly different angle. It's actually quite phenomenal that such a simple thing would work. Visibility doesn't quite go to 100%. It does go down to 0. So it's nearly perfect visibility as I tune the angles. And this allows me to mark every single path. And from this laser, what it means is I can generate an 8-dimensional state. So it's classical light, but it looks like an 8-dimensional quantum state. And, you know, the GHZ states, if you don't know what they are, you can go and Google it afterwards. But the GHZ states are the basis states for an 8-dimensional Hilbert space. And so we can show that you can generate GHZ states directly from a laser. And you don't need anything more than 2 simple mirrors that you could get from Thor Labs. So structured lights even very complicated structured light does not need complicated structured matter, and it does not need complicated solutions. So I think I have time to go to the last part of the talk, which is to say that even though I'm referring to this as high-dimensional classical lights, and its GHZ states, it doesn't replicate a quantum process. So I believe very strongly in the benefits of classical entanglements, but I don't believe that classical entanglement can replace quantum mechanics. And the reason is this. So here's my cartoon of a quantum process. We have an ultraviolet, let's say, nonlinear crystal. This would be the usual way to generate entangled photons. And out come two entangled photons in the infrared. And they're going in different directions. So this idea of non-locality cannot be replicated in the class. But still, I can take all the tools that I showed you and apply it to this problem. So how do I do that? Well, here's my cartoon. Oops, sorry. Cartoon. There's some light coming into it. I'm going to generate two entangled photons. And I'm going to control what those photons are with spatial light modulators or DMDs or whatever I choose. And then I'm going to detect the photon incidence. And so what I like to say, I like to call this quantum mechanics with pictures, because I can use the Hermite modes as what I project onto the SLM, or I can use the Laguerre modes. The thing about quantum mechanics is that what you have is what you choose to measure. So by measuring this photon in a particular state and measuring that one in a particular state, that determines how angled. All this quantum mechanics with pictures, because I'm really just using holograms or patterns of lights as my basis to describe the entanglement. Because if I go back here, I say these photons are entangled in what basis? So by choosing these patterns, Hermite or Laguerre modes, I can choose the basis and therefore choose how I describe the entanglement. So to do that, everything comes down to how I made the measurements. And so what I need is a pattern-sensitive detector. I need a detector that is sensitive to only particular patterns. And that I can do by just running all the beam shaping things I told you about earlier, but in reverse. So if I had my blob of light and it went through a hologram and it generated, let's say, a Bessel mode, then by the reciprocity of lights, if I come backwards through the hologram with the Bessel mode, it must come back into the Gaussian. And the wonderful thing about Gaussians, the only pattern that couple into single mode fibers. And so the hologram with a single mode fiber becomes a pattern sensitive detector for quantum photons. So to know how that works, let's again use our orbital angular momentum example. I have my UV light coming into the crystal. Let's say I have no angular momentum to begin with. You can change that case if you want, but let's take it as a simple example. Well, the orbital angular momentum of photons A and B that come out, the photons that come out, they must add up to the pump because orbital angular momentum is conserved. So now the question is, how many ways can you add two numbers? There are an infinite number of ways. I could have 1 and minus 1, that would work, but so would the opposite. I could have 2 and minus 2. I could have 3 and minus 3, and so on. And so if I write out the states, it's an infinitely long state. So in other words, in theory at least, it should be possible to get to infinite dimensional entanglements using patterns of light. And that's simply because there are an infinite number of patterns that you could possibly use. So the first person to do this was Anton Zeilinger. He used physical diffractive holograms, not spatial light modulators. And he did exactly like I showed you in my cartoon. He's got two holograms and he measures them with his fibers. And here you see you've got the middle one. When his pump is 0, he's got measurements at 2 and minus 2, 1 and minus 1, 0 and 0. In other words, on this anti-diagonal. And if you change the parameter, then the diagonal shifts. So this confirms that indeed you have conservation of AM, and he also showed that they were entangled. Today, of course, we do it now with holograms. So I have two holograms, hologram B, controlling photon A and photon B, but it's controlling it in the measurements. And so what's going to happen with OEM is I'm going to change the hologram over here while I measure some hologram on B, and then I change it this one and so on. So I keep changing what I'm looking for. Where it stopped now, it would say look for OEM of 1 on A and look for OEM of 3 on B. So what would you get? So here's the answer. This is an experimental image. And so you see that when I measure, say, -10 on photon A, I don't count anything until I get to +10 on photon B. And vice versa, 10 on A is -10 on B. So a very strong anti-diagonal. And what I like to tell people is that if you didn't know it before, then I can confirm for you now that, remember I told you it's an infinitely large Hilbert space? Well, if you didn't know, then infinity is about 20, at least in our lab. And our lab is very typical of all labs. Now you might say, well, 20 is very far from infinity, and I will agree with you, that's true. But 20 is also an order of magnitude bigger than you get, which only gives you two-dimensional states. So even though we can't quite get to infinity with our patterns, we can get orders of magnitude bigger than you could just get with polarization. So that's why we like it. And now what can you do with these entangled photons and patterns of light? Well, you could replace Elaine Aspect's experiment from 40 years ago with a digital equivalent. And what Elaine did was he turned two polarizers. He used polarization of light, the conditional probability of making a detection. In other words, saying, if I projected photon A into a particular polarization, what's the chance I would get something on photon B as I rotate the polarizer? And the classical correlations, this conditional probability curve would oscillate around the quarter mark. It never goes to 0 and it never goes to 1/2. But if you have quantum correlations, then the conditional probability oscillates between 0 and 1/2. So this is very nice because you can see just visually which case you've got. And here's a picture from his paper. And you can see that although there's some experimental uncertainty, I think we can all agree that this curve is 0 and 1/2. So this is a clear indication of quantum correlation. And we can now do exactly the same thing, but instead of turning polarizers, we rotate holograms, and in our lab, the oscillation again goes from 0 to 1/2. A little bit noisy, but there's no question that this is quantum correlations. And actually, this was done with Bessel modes. So we can replicate what we can do with polarization, but we can do it in high dimensions. Why would we care about that? Well, high dimensions means more information in every photon, so high information capacity in a communications link. High dimensions means better security, and higher dimensions means more robustness to noise. So there are many, many good reasons why going to high dimensional quantum states is a good. Now, there are many ways to get there. You could also get there with time frequency. So why use patterns of light? Well, one of the reasons is that some of the benefits of the classical properties of patterns also come through in the quantum world. So take this example. I have an axicon. I put a Gaussian beam through it. I generate a Bessel beam in this cone region. And very famously, if I block part of the Bessel beam, there's a shadow region, but then the Bessel beam reheals. So we talk about self-healing beams. Actually, Sabino has shown that this is not only true for Bessel beams, but actually for many types of modes. But it's most famous with Bessel modes, I would say. And here's a picture of the Bessel beam. It's been blocked. There's a shadow region, and some distance later, it starts to self-heal. Now we ask what happens in the quantum world. So let's have a look. Here's my quantum cartoon again. And what I'm going to do is I'm going to block the photons over here. And what do I see? Now notice that the block, excuse me, has come before the spatial light modulators. In other words, we have not yet told the photo they're going to be, whether they're going to be LG or Bessel. And so we only tell them after they've passed through the aperture. When we tell them afterwards that they're LG photons, then we find that the noise level stays very low. The signal, stays very low. But if we project into Bessel photons, we find that after the shadow region, which is shown here in this yellow, then the coincidences pick up again. So we get quantum self-healing. And we can see this quantum self-healing if we look at the density matrix of the states. And if you don't know what that is, don't worry about it. It's a way of visualizing how the quantum state looks. So here you see initially it's very pristine. Everything's like nice and regular. But then we block the beam and it becomes totally noisy. But after the self-healing distance, the quantum state returns back to a high fidelity, not quite as perfect as before. You can see that the little bars are not quite the same, but pretty close. And so that lets us do all sorts of cool things. So, for example, we can do quantum key distribution through obstacles to not only pack lots of information into the photons, but also to transmit through systems that would not usually transmit it. And I want to end now by giving a message to the students. Because whenever we give talks like this, we always almost suggest that everything is done and dusted, which is certainly not the case. And so here I show you where we stand. You know, we can create lots of beautiful modes, but we can only detect deterministically in 4 dimensions. We've only been able to teleport 3 dimensions. The bit rates with patterns of light is as close to 0 as you could care to be, so let's just call it nothing. The distances are tiny compared to what we have to do. I mean, hundreds of meters or perhaps a kilometer, but not more than that. And so you see that there's a huge void that needs to be filled in using structured light at the quantum level. And if I show you another cartoon of it, we can go up in dimensions, but only using 2 photons. Or we can go up in photons, but only using 2 dimensions. And there have only been 3 studies, we've got one of them, that pushes both the photon number and the dimensions simultaneously. Huge gap here that's totally empty. And so just as with the classical case with nonlinear optics, there's a huge opportunity here in the quantum world as well. So I want to come to the end. It took a little longer because of the disruption with PowerPoint. I apologize for that. It's been a little bit fast because I wanted to cover a broad spectrum of topics to make it interesting for a wide range of listeners. If it was too fast for you, then we've got these recent reviews on quantum, on lasers, and general structured light. And so go ahead and read them. They should give you a much more popular review, and it will highlight all the fantastic work that other groups are doing, because there's a lot of work out there that I simply haven't been able to mention at all. These were published very recently, but if you want to see a really recent version, then go to this month's issue of Nature Photonics. We have just put out a review article, and it covers everything that I understand about structured light. So if it's not in there, then I probably don't understand it, and that means that there's a good reason for you to study it going forward. On that note, I want to thank all my collaborators who have contributed to all our successes over the years. We love to collaborate with people, so please give me a shout. In fact, we love to have students visit our lab, and we love to send our students out to other labs. And so here's a happy waving photo of my group. Pre-COVID days, I know now, but because a few faces have moved on, but nevertheless, you know, we're a young, vibrant group. We love to host students. We love to send students out. So please do give us a shout if that's of any interest to you. And I think with a slight delay, I'd like to thank you for listening.
All right. Thanks a lot, Andrew. Thank you very much for this fascinating talk. I always love your talks, and this was no exception. There are a few questions. Before I read the questions, I want to tell you something from our current director, Rafael Espinosa, who says, "Welcome to your house, Professor Andrew Forbes." So you know this is your house. And then Ruben wants to launch the first question. So please, Ruben.
Hi, thank you, Professor Andrew, for this wonderful talk. I really enjoy it. It was very clear. And my question is, I've seen your work on beam propagation in high scattering media, and I wonder if you can comment what kind of parameters are relevant for beam propagation in scattering media. Is just enough to have a structure beam or a vector polarized beam? What is more important in your opinion? Thank you.
Right. Great. I'm going to switch off my video just to make sure my signal remains high, but I will switch it on as the question is asked. So in fact, we've done a lot of work in turbulence more than scattering.
Right.
Looking at multiple phase aberrations. Excuse me. In that case, it certainly is true that vectorial light is very good because the spatial modes decay, but if you have a phase perturbation to each component of the vector mode, it can be factored out. And so the polarization structure remains invariant. I would say in a scattering media, you would have to look for something that each polarization component behaves similarly so that a commonality could be factored out. Then you would look for something that's recoverable after that. So Ruben, to answer your question, I don't know the direct answer, but I do know what the question is, and it's exactly what you asked. Whenever I approach a topic, I always say, how many degrees of freedom am I using at the moment? And then I say, would there be any benefit to the other degrees of freedom? For example, you know very well that when people go through scattering media, they use time. If you time gate your detector, you can find. So using time as an extra degree of freedom helps you. Would polarization help you? My gut feel would be yes. I cannot think of any reason why not. You just have to find the right mechanism to exploit it.
Right. Okay. Thank you very much.
Thanks, Ruben. There is another question, Andrew. It's written, so I will read it to you. It's a very long explanation. First, I guess, to put you into context. And the question is, it's short. So I would read to you. Thanks for your interesting talk. For a long time in polarization holography, polarization spatially modulated patterns resulting from coherent superposition of orthogonally polarized beams have been recorded in photoacoustic polymer films. In fact, holographic polarization gratings are used to analyze the polarization state of laser beams. A proposed application was a polarization holographic lens having two focal points with orthogonal polarization states. And the question is it possible to record a structural light hologram to obtain two vectorial fields with orthogonally spatially modulated polarization?
So to have two orthogonally polarized fields with?
Is it possible to record a structural light hologram to obtain two vectorial fields with orthogonally spatially modulated polarization?
I'm not sure what is meant by two vectorial fields. You can certainly create a field where each polarization component can have any arbitrary combination of modes. And in fact, Carmelo, you have shown how to do this with DMDs, right? Mm-hmm. But I wouldn't say, if you have two vectorial fields, you can always combine the polarizations back to one field. So you can view them as two fields, and you can split them as two fields. Say that there are two fields, I wouldn't be convinced. You know? In the same way that if I took a single scalar OEM beam, I could say that there I have two vectorial fields. I have an equal weighting of as polarized light. But no one would believe me if I said that.
Yeah, I guess, yeah. If you could clarify a bit, Geminiano, your question, if Andrew answered correctly what you asked. Meanwhile, let me go to the next question, Andrew. Thanks for the talk. Could you talk something about super resolution using super oscillations, please? Yes.
So I've actually never worked with super oscillations, as it happens. But I've read some of the work of Michael Berry, and he's. I'm going to switch my video fanatical about it. And actually, I was just chatting to Miles Padgett the other day, and he's also going into it. Yes. So super oscillations allows you to do crazy things. One of them is to go down in resolution. Another is to hold lots of information in the field. But even though you don't need the typical bandwidth that you would need in a typical Fourier system. The problem, as I understand it, is that to reach these super oscillating fields, you in principle need infinite energy. It kind of comes down to the Bessel problem again. So once you start to envelope the field, you cut off the oscillations, and so you limit what is possible. But exactly how far you could go, given that you have some approximation to the field, I don't know. I've never played with that field yet. But if you're interested, have a look at Michael Berry's work. He's put a lot of theory behind it, and you can see what's possible and what's not.
Great. Geminiano, would you like to rephrase your question somehow? Yeah, he probably doesn't have a mic. Okay.
Just going back to the question about the vectorial fields, the person who asked the question gave lots of examples of what you could do, and it's absolutely true. When Benjamin was in my lab and we did this lovely polarization fringe story, we were so excited to discover that Woods already knew this 100 years ago.
Yes.
So I think it's very typical in optics that we tend to reinvent things.
Yes, that's true. and now, especially that we have digital devices, we can do it perhaps easier than it was done in the past. Okay, so Andrew, his question is the following. My interest was at the reconstruction. In holography, you get two conjugated images of the hologram. But anyway, okay, so he will contact you later.
Brilliant.
Yeah. Okay, there's another question, Andrew. How do you obtain experimentally high-order Bessel beams?
Okay, good. Yeah, that's actually a good question. So there would be several ways to do it. You could encode the function directly. That would be a one-step approach, in which case you would have amplitude and phase modulation. Historically, if you go back in the literature, then the way people would do it is they would make a phase-only device, maybe a Axicon or a spiral Axicon on a digital Axicon on SLM with an LG beam. So you would, rather than go with the Gaussian, you'd get the L as LG beam. You go in with a high order OEM, and then that gives you the L in the Bessel. The one step with the Axicon, because it's only phase and one step, it also leads to only approximations. If you really want to do it, amplitude and phase control is the best. Yeah.
Great. Thanks, Andrew. That was the last question. We don't want to take more of your time. It's time for dinner, right? Stefan Steph and who was? Well, they're waiting for you for dinner, right? So
Yes, no. For all the listeners out there, it's 7 p.m. here, and yeah. So,
yeah, exactly.
but it's been lovely to chat, and really, I've thoroughly enjoyed it, and I want to thank you once again for the invitation. I really appreciate it.
Thank you very much, Andrew. Lovely talk, and it's a wonderful talk. Thank you, everybody, for coming to this colloquium, and enjoy dinner, Andrew.
Thank you, everybody. Take care.
Bye.